Okay, now we are going to discuss the 4 different mechanisms that help non-LS communication. We know that non-LS communication is possible because of 4 phenomena: penetration, reflection, diffraction, and scattering. Now, we'll have short discussions on each of these 4 things now. But you need to understand that non-LS communication is basically, it also involves LOS communication. Like when you have reflection, please, pay your attention. When you have reflection, then from the source, the signal is traveling and it is on incident on the reflector. Then the reflected signal goes to the receiver. But you definitely have an LOS communication between the source and the reflector first, right? And again, after the reflection, the reflected signal, okay, of course, it will be less than what was incident on the reflector. But this incident signal will again propagate like an LOS communication. There can be even, few other things also on the way in non-LOS communication. But with this typical example, okay, if you just have one reflector between your transmitter and the receiver, then the reflected component will again travel to the receiver, and that will be another LOS communication. So it's actually a combination of 2 LOS communication and a reflection in between. Okay. So the discussions on, we'll sometimes discuss some methods specific to LOS, sometimes some phenomena or methods specific to non-LOS. However, you need to understand that whenever it is non-LOS, then there are LOS communications or LOS phenomena also involved. Okay, non-LOS has a lot of LOS paths. Okay. And also you have these mechanisms like penetration, reflection, diffraction, and scattering. But around this phenomena, you have actually LOS propagations. Okay. So with that in mind, we'll talk about those four things. First, we will have a short discussion on penetration. Uh, okay. If we think of buildings, okay, then most of the time the penetration actually affects our reception because we are in buildings, or uh, the building surface and building materials affect. So if it is the building surface area, okay, then it is called building penetration loss. And it's also sometimes called outdoor to indoor reception. Assuming that you have an external transmitter, you have a transmitter external to the building. For example, if it's a mobile tower, you're receiving signal in your mobile phone. So the signal will actually have to come to the building first, then it has to penetrate the building surface, okay, which can be wall or window whatever surface material you have. Okay, and then you have actually some penetration loss. Okay, this surface will consume some of the energy, and the rest will be available on the other side, that will again propagate and get to the receiver. And the loss that you have in the building surface, okay, is called building penetration loss, or BPL. And it's also called outdoor to indoor loss, or O2I loss. Let me write it down in the chat box. Okay, outdoor to outdoor to indoor. Okay, which is also called O2I or BPL. Sorry. Okay. So synonym of BPL is O2I loss, or outdoor to indoor loss. And this loss largely depends on three different things. The material of the, well, actually for any penetration case, whenever you have, even if it is not building, maybe, I mean, you are, say some trees can also offer some, whatever obstruction you have between, maybe say you are next to some shade at a bus stop. Okay, so whatever you have as the shade is uh, I mean is an obstacle between the source and yourself. So the material has the signal has to penetrate. Okay, so in any case, this penetration loss depends on three different things. Basically, the material of the abstraction, the operating frequency of the signal, and the thickness of the abstraction. Okay. Now, the term BPL is very common used. Okay. The penetration loss depends on the properties of the material and the various modes of interaction between the signal and the material. Now, this uh, will actually, this can be something specific to a particular type of material and a particular frequency. Okay. So the it depends on these things, how the interaction will take place. So there will be some amount of absorption because of, I mean, for example, if there is any transition from one energy state to the other, okay, so that way energy will be consumed. So there, it depends on the material type and frequency, how these things will take place. But commonly, if you have more uh, density, okay, I mean higher molecular density in the material, then the absorption of energy is higher. You have more occurrences, okay, I mean, say the change of transition states or whatever, all these things occur more and you have more absorption of energy. So on the other side of the material, you get less energy. And the frequency, you know, I mean, affect because the wavelength is relates to this energy state transition, or if there are any resonances. Okay, so these things depend on the wavelength of the signal. So anyway, usually if you have shorter wavelength, okay, then this match better with the with the length or the the distance you need there for the change of the transition states, or any kind of energy absorption. So usually at lower frequencies, mm, uh, usually at higher frequencies, okay, when you have shorter wavelengths, then there are more chances of energy absorption, or your energy absorption increases, okay. But this definitely depends on the type of the material, okay. uh, as we'll demonstrate using some examples, okay. It can happen that for a particular type of material, at a higher frequency, you have lower absorption, okay. So sort of erratic. The estimation of penetration losses have been made through different tests, okay. It's difficult to predict using theories, and so it is largely dependent on tests, and a lot of tests have been made, and of course there are analysis, and there are theoretical discussion also, okay. uh, but among the different building materials, okay, if we check the condition at the lower frequencies, okay, because this the very widely tests were done before up to 10 gigahertz, which is the usual range of wireless communication, okay. So now you see that the with different types of building materials, the penetration loss gradually increases with the frequency, okay. And you can also see that the penetration loss is very high for the two things, brick and concrete, which are heavy materials. Heavy materials means they have high molecular density, as we are stating that higher molecular densities would offer more penetration losses. So a heavy material, okay, has a high density, and so you have more losses. However, in the case of brick, the loss is pretty much constant over this whole frequency range. But see how it is changing in the case of concrete. Okay. It's sharply increasing with the frequencies. Uh, and so the usual communication nowadays uses frequency in the order of gigahertz. Okay, so it is higher than. So you can see that uh, for our, well, of course there are communications, and it's not usual. Say the radio broadcasts. Okay, in that case you have very low losses, and concrete also offers low losses there. Okay, but if we talk about Wi-Fi or mobile communication, the modern uses of wireless communication, then concrete is the worst enemy uh, for wireless communication, as demonstrated here. Okay, so the frequencies are in the order of gigahertz. Okay, a few gigahertz, uh, around 2 gigahertz or higher. So then you see that concrete is behaving the worst. Nowadays, a lot of estimations are being made for high frequency applications, uh, mainly because, these estimations were not made before. So now you are using high frequency, so you need, so a lot of activities are there. And secondly, for low frequencies, you had a small range, like up to 10 gigahertz. Okay, so the tests were also, I mean, uh, the activities uh, you need there is not as much as you need for high frequency, because you have a very wide range up to 100 gigahertz. Okay, so when you have some setup for testing, it may cover a particular range. For another range, you need another setup. So different people have done tests at different uh, ranges within this, say from 10 to 100 gigahertz, within these high frequency ranges. Different people have done tests at different ranges, and a combination of all of them can give you the whole variation up to 100 gigahertz. And let me tell you that there are actually, I mean, I told you before that in the research lab, there are activities up to 300 gigahertz. Okay. So there are really a lot of activities above 100 gigahertz. There are different bands. Okay. E band, G band, different bands are there. I'll give you some, I mean, the uh, frequency ranges for this very high frequency ranges. I mean, these bands are actually used mostly, they are used in the research lab nowadays, up until now. But shortly there will be, in near future, there will also be commercial uses. Okay, so there are activities. There are a lot of activities in the research area above 100 gigahertz. Okay. Uh, now, an example of penetration losses, BPL, building penetration losses, because it can affect your signal reception a lot. And I think all of you have the experience that inside a large building, you had very poor coverage. You suffered from low quality voice calls or poor data rate. Okay, so you have the experience of the impact of penetration losses. Now see that the new buildings are affecting you more. Okay, a lot more. The key point here is that you have better temperature control in the in the new buildings, and for this purpose, for the purpose of temperature control, they use this infrared reflective glass. Okay, I mean the black uh, or the gray glass that we see now. So this glass offers low energy consumption with air conditioning of the building. When I mean, you know, the commercial buildings especially are nowadays all air conditioned. And if you have good leakage of energy, if the energy radiates out of the building higher, then the air conditioning cost will improve, will increase. Okay, you will so to reduce this energy uh, losses, okay, or I mean to reduce the energy consumption, electric energy consumption, the buildings are made with IR glasses, infrared reflective glasses. Also, they look better, and the light, I mean, from architectural requirement, they are also better. Okay, so there is a difference from the old buildings which use the typical clear glasses. Now you see that actually there is a, I mean, I have some data comparing the loss in the clear and higher glasses that I'll show, but you see the overall penetration loss Okay, because of this difference. I mean, you have, well, it is true that the old buildings have more walls, okay, and uh, the windows are less for old buildings. In the new buildings, you have large windows. Okay, so when you have brick walls, then they can also prevent your signal a lot. So in that respect, old buildings have higher penetration loss. I mean, when you have walls on the surface, okay, so the windows can allow more penetration of the energy of the signal. However, although you have large windows, okay, they don't use clear glass, they use IR glass. So the overall effect has higher penetration loss on the new building side. Okay, so because people might argue that you have more windows in new buildings, so you should have better signal. Okay, but this is the other way around. Now you see that at 28 gigahertz, the penetration loss was found to be, yeah, uh, 40 dB in IR glass and 3.9 dB or around 4 dB for clear glass. So almost 10 times more losses are there. Okay, I mean, it's not uh, that bad for low frequencies. Okay, but at 28 gigahertz, the difference is actually very wide. The IR glass is offering 10 times more losses. Okay. Now, for brick, we have okay, the pillar. I think I may be a little bit mistaken because the pillar should be made of concrete. It's not brick, right? The indoor drywall is made of brick. Okay, please consider this correction. I mean, this 28.3 dB loss we have through a pillar, which must be made of concrete. Okay, and in the case of indoor drywall, it is made of brick. You have a loss of 6.8 dB. So again, you see there is a large difference. With, okay. So I mean, all these differences are a lot more for high frequencies. Okay. So the conclusion is that in the case of high frequencies, the outdoor to indoor communication can be very difficult. Okay. I mean, we already have difficulties with the penetration losses at the surface or outdoor to indoor loss. Sometimes we experience difficulties. But as people will be using 5G or high frequencies, these difficulties, I mean, there'll be more challenges. Okay, it's up to the operator how to take care of everything. They have to make sure that we receive signal inside. Okay, so there are different techniques that we'll discuss later. But you see, the challenge is a lot more. Okay, for high frequencies. Now, the second paper here shows that interestingly, for these high frequencies, the loss in the concrete and the wood is almost the same. Okay. Of course, I mean it was when concrete offers much higher losses at low frequencies, but in this case, I mean we have for the wood actually we have this type of data. Okay, this one shows a comparison of losses in different types of materials. And see, IR glass offers very high losses, and regular or clear glass, okay, has low losses. In the concrete, for concrete, we earlier showed that up to 10 gigahertz, there is a sharp rise of the loss. Okay. Now here we can see the variation uh, over a little longer range, up to around 15 gigahertz. It continues increasing that way. Then maybe it is stabilizing. Okay. Okay. So kept increasing. It also shows some uh, comparison among different types of buildings now. Okay. This black dot, rectangular dots represent building with IR glass. The lines, okay, vertical lines represent some range. Okay, I mean different test results were found, and so some range is shown. Okay, so vertical lines shows a range of different results, maybe for different types of buildings. So, and this blue circle dots show data for building with clear glass. Okay, so you see the difference. And I think the high loss model represents buildings with IR glass, or I mean the new type of buildings. Okay, and the low loss model gives you the variation of BPL for all types of buildings. Okay, or buildings with clear glasses. So again, there is a variation over up to high frequency, up to around 100 gigahertz, and I mean some data for different types of buildings, residential and university campus building. Okay, now this one is a good collection of many different types of building materials. Okay, and the tests were done at very promising 3 frequencies in the high frequency range, 28, 39, 73. For the 5G deployment, these frequencies are considered potential, around 20, especially the 28 gigahertz, okay, will be one of the first deployments. Around 38 gigahertz, 39 gigahertz, okay, some preparations are there, so especially these frequencies. 73 gigahertz will also have deployment, but not in the near future. Now you see that at these frequencies, okay, I mean the blue one represents the loss at 28, then the orange one at 39, and the gray one at 73 gigahertz. So for any material, usually you have the high loss at higher frequencies. Okay. Blue is short, then the orange has medium length, and the gray is the tallest. Okay. So this the usual case, but there are some exceptions. Like here, there is a material called paver brick that is used for pavements. In this case, the 39 gigahertz is offering a high loss pattern. Okay, the loss profiles are shorter than, so there may be some resonance or something around that frequency. Okay, also the last example has similar profile. You have very high loss for the mid frequency around 39 gigahertz. So Usually you have, as I mean this type of exceptions you'll also find for some materials here, like this window with double pane, this vinyl sliding. Okay, some exceptions you have there. So anyway, as we were stating before, or we are hinting that typically you have higher losses as you increase the frequency, but depending on the material, there can be some differences or some exceptions. Okay, questions. So with that, I'm gonna complete the discussion on penetration loss. Questions?
No questions, sir.
Okay, thank you. Now we will have a discussion on reflection, but I mean, in this case, I will actually discuss some common wireless propagation calculation technique, or I'll derive some formula, and in one of the case, one of this derivation, there is a reflection. Okay, so I won't discuss any discuss something specific to reflection, rather some calculation, I mean derivation for receipt power calculation will involve a reflection on the way. Okay. However, the first discussion will be for pure LOS communication. Okay, will be for pure LOS communication. And in the second part of the derivation, there will be a reflection. This part will derive a formula called freeze-free space equation or link equation. Very common. I mean, one of the fundamental relationship for wireless communication. At the end of this discussion, we will derive this one, which is called the, I mean, this is the typical, I mean, this is the form of equation in normal unit. Okay, but we can also show all of them in dB. I'll tell you how the significance of dB. Okay. So here PR represents the receive power. Okay, we have some transmitter then, and which is sending power, and you are receiving power at the other end. The received power we are interested in usually, right? So that is called PR, and the power you're transmitting from the transmitting end is denoted as PT. Okay, and then you have some antenna for and the transmitting and the receiving end. This antenna has some directivity, which we'll call gain. Okay, so the gain of the antenna at the transmitting end will be denoted as GT, and that at the receiving end will be denoted as GR. D represents the distance between the transmitting and the receiving end, and lambda is the wavelength of your signal. Now these notations, okay, are very common for wireless communication, and throughout the course we'll be using the same notations. So D will be representing the distance between the transmitting and receiving end, okay, in all of our examples. So all these notations we'll be using throughout the whole course. Now we start this way, that we first consider an isotropic antenna at the transmitting end. Okay, please give me a second. sorry. So the isotropic antenna is emitting energy equally in all different directions. And here we have the receiving antenna, okay, at d distance. The physical area of the antenna is A. Now, we are interested in how much energy we get at the receiver, right? So first we need to check how much energy we have here. And that we know that the energy will be equally distributed in all different directions. So if you consider a sphere, okay, then we can find the energy concentration here. The total surface area on the sphere is 4 pi d square. So per second you are emitting pt energy, pt joule of energy. Okay, so the energy concentration or flux density, okay, power flux density at the receiver is pt over 4 pi d square, right? Let me know if you have any difficulties in understanding. Very simple.
No, sir, it's fine.
Yeah. However, we know that let's consider a directional antenna. So we know the location of the receiver, and we are directing our power in that direction. So that is the practical antenna. We have a directional antenna. So then definitely, you are not wasting your power emitting them in unnecessary directions. Rather, you're trying to focus. Now, the gain of the antenna tells you the ratio between how much power you are actually sending towards the desired direction compared to what it would be if you had transmission in equal in all different direction like an isotropic. So GT is the ratio, right? So if I multiply this one, this F.
Sir, can you explain the GT again, sir? One more time.
GT say we discussed directivity of antenna before, right? And
Yes,
probably you remember that is the ratio between the power at the both side. The power at both side means the power that you are sending. There's the desired direction. You have the direction of the maximum radiation. Okay.
Yes, sir. Okay.
So, and it was ratioed with the power that you would have if you had an isotropic antenna instead. If you had an isotropic antenna instead. So that's so meaning that if you since in the first example we had isotropic antenna, okay. So if I multiply by G the directivity, then I would get what I have with directional antenna, right? GT is the ratio of what I get at the direction, at the both side or at the desired direction or the direction of the maximum radiation compared to isotropic case. Okay, compared to the same power, but transmitted equally in all different directions unnecessarily. Okay. So the power will actually increase. I'm just collecting the whole power towards the direction of my receiver. Okay, from the first figure to the second, the difference is that in the first figure the energy is radiated in equally in all different directions. Now the same energy PT will be sent towards the desired direction, okay, using a directional antenna. So definitely in the desired direction, in the direction of the receiver, the energy will increase. But how much will it increase? It will increase by the ratio of the directivity, because directivity is the ratio of maximum radiation compared to what we have for isotropic antenna, right? So multiply by the directivity and then you get how much the power will increase, okay, from the first figure to the second figure at the receiver, right? Is it clear?
Yes, sir.
Okay, so that directivity we call gain, okay.
Okay, sir. Yes, sir.
right? I explained before. And on the transmitting side, it is GT. So multiply by GT. So this is the power we have here. So this is actually the power density, the amount of power, the power per unit area at the point of the receiver available in the air. In the air, over per unit area, this much energy is flowing per second. Okay. Now, the power that is intercepted by the receiving antenna depends on the area of the antenna. Okay. So F multiplied by A. Okay, very good. But we know that actually it is not the physical area that impact. Rather, the power we get at the receiving circuit depends on the effective aperture. Okay, we discussed effective aperture, which tells you, okay, if you, if if the amount of power is incident on the effective aperture of antenna, then you actually get how much power. Okay, from this calculation you get the amount of power that is delivered to the receiving circuit. So we need to multiply by effective aperture, not the actual aperture. So we have to multiply F by AE, then you get the received power. Okay, very good.
So the
Now,
effective aperture is that part where the energy is going.
no, it is not that part. The energy is incident on the whole antenna,
Yes, sir.
but but
It's like an average, sir.
it's not. It's not. It doesn't work that way. Actually, the antenna design, the antenna can have many different forms. The antenna design tells you how much power it can collect.
Okay, sir.
Okay, like it's again actually the directivity of the receiving antenna.
Okay, sir.
If your receiving antenna is more directive, then it will collect more energy. You have the same energy available here at the receiving end position,
Yes, sir.
but it depends on the uh, receiving antenna, how much you like. Here in the class now, I am delivering something and the same thing is reaching all of you, but some of you are more attentive than others, so they are like focusing more, so they can capture more. So it is again, the same antenna design is used on both sides.
Yes, sir.
And the directivity works equally. If you
Yes.
uh, if you improve the directivity on any side, you will get equal benefit. Okay, so that directivity you can also relate to effective aperture. Okay, how much energy you are actually getting. This is like, an equivalent area. You calculate that, okay, if I calculate say all the power available here, okay, the same flux density, power flux density available here, if it is incident, if it was incident on this area AE, effective aperture, okay, then you would get certain power. That is the power you actually get when the power is incident on the whole physical area, but because of directivity,
Yes, sir.
you get that less amount. Okay,
Less amount of area.
yeah.
Yes, sir. I understood.
So
Yes.
definitely AE is smaller than A.
Yes. But receives the same power.
Mhm.
But receives the same amount of power that the entire
Right,
thing would have received. Yes,
right,
sir.
right. So since AE is related to directivity, okay, there's a relationship between the directivity or gain, okay, like this. We presented it without any proof in our entire discussion. So we can use an expression here. We'll replace AE by GR lambda squared by 4 pi. And that gives us, after rearranging, you get this expression. Okay. So now see that the power. So this is the LOS communication, the fundamental relationship for LOS communication. Then title, please remember freeze equation or link equation. So you calculate the receipt power by multiplying PT, GT, GR, okay? And then divide it by 4 pi D by lambda whole square. Okay, that's how you calculate. Now, a couple of things. First, PTGT, this term has another, this multiplied form has another term, EIRP, effective isotopically radiated power. See, we had PT amount of power radiation. Okay, this much energy per second you are radiating. But that's not what we are interested in. What you are, what you are sending from the source end. It actually matter what you have as PTGT. From the receiving end, you are interested in how much PTGT is, how much you're sending towards me, right? And that is from the receiving end, you may want
Yes,
to
sir.
ask what you are sending. Okay, I don't care what you are sending in other directions. So what your
Yes.
PT is, okay? Rather what your PTGT is, because that tells you what you are sending towards me,
Me.
towards myself, right? The receiver can say like that. So this is what you are effectively sending. Okay, effectively you're sending PTGT. So, but it is, compared to the isotropic case, so it is called effective isotropically radiated power. Okay, so EIRP. We actually discussed this term in our lab class last time. Okay, and secondly, the denominator is called path loss. You said that the in the numerator, all the terms you have, as you increase, your power reception increases. Definitely, that should be the case. Linearly, they will increase. If you increase the transmit power, your receive power increases linearly. Increase GT or GR, okay? They increase your receive power. Now, in the denominator, you have the distance, and we know that if the distance increases, our power will decay. But how it is affecting, okay, that depends on the environment. In the LOS case, where you have no other obstacles, or you don't consider any objects around, okay, it's free space equation. Okay, just you have a free communication link with no objects around. So in that case, the distance affective this way. Okay, from our derivation we can see.
So one question, sir.
Yeah.
Yes, sir. Here you wrote 4 pi d by r, right, sir?
D by lambda.
D by lambda, sir. Shouldn't it be 2 pi?
Yeah, it looks
Oh,
like
no,
that.
no, sir. Oh, no.
But it comes from the fact that on the sphere, the surface area is 4 pi d square.
Okay. So,
Okay.
my bad. Yes.
So the key point is it is inversely proportional to d square. Okay, so that's the key point, d square. The second key point is you also have lambda here. So there's also, it's d by lambda whole square. Okay. So anyway, the denominator actually tells you how the distance, or okay, the path what you have on the way is affecting your reception. So this is called path loss. This whole thing is called path loss. Okay. Now, the engineers commonly want to use dB term. In dB, you take log and 10 base log, and then you multiply by 10. But please give me a second. Okay, I'll write on the writing pad. don't know, but sometimes this writing pad causes trouble. That's why I don't always connect first. Okay. I don't know what the problem is. Mm, okay. Okay. Let's forget about this writing pad. Okay. I uh, we go back to our slide here. I will I mean just try to orally explain, and later I can share something, write down something and then upload. Okay. See, I just wanted to explain what I mean, wanted to make sure that you understand DB clearly, because we'll be using DB in most of our problems. The information may be given in DB units, not the usual units, and also the results you most likely calculate in DB. Now, okay, just give me 1 second. I need to stop something. Sorry about that. Okay, now this DB calculation uses a reference, For peer, when you use DB, you need to use a reference, and that can be 1 watt, 1 milliwatt or something. Most likely for wireless communication, we use milliwatt as the reference because the receive power level is too low. Okay, so if your power here is say 1 watt, you divide 1 watt by 1 milliwatt and then take 10 base log, multiply by 10. That's how you get the power, receive power in dBm. Okay, in dB. But just to show that it has used the reference milliwatt, you write down as dBm. Okay, got it?
Yes.
On the other side, again you have log 10 base log. Okay, and for the whole thing, say, I mean, consider this term. For the whole thing, you divide by 1 milliwatt. Okay, 10 base log 1 milliwatt. Okay, this just try to understand that you are dividing by 1 milliwatt only once, right? Only once. I mean, on both sides. I mean, here also you have 1 milliwatt reference to represent this whole power. But when this whole power you are considering as a multiplication of different components, then you can also show this way that, okay, PT by 1 milliwatt into the rest. PT by 1 milliwatt multiplied by the rest, GTGR by 4 pi d. Okay. And then with this log base case, okay, you can, or let's assume PTGT, okay. With the whole thing, logarithm, you know that if your argument is has multiplication for log, then you can show them as summation. If you separately, the log terms can be shown as summation, and for the denominator it will be subtraction. So here this, I mean, PTGT, which we are calling EIRP, EIRP. Okay, you can separate, and the rest you can show, but they all are shown as actually in dB form. Okay, they all are in dB form. Now this
Wouldn't it?
with this PTGT, if you keep that 1 milliwatt PTGT by 1 milliwatt, okay, and the rest you are showing, everything is shown as dB, but of course 1 milliwatt you can keep with one of them, not all. Okay,
Sir,
if you, yeah,
will not this cause an error, sir? Because
no,
some
it is
variable has milliwatt that divided the others.
no, actually the whole thing you are showing in dB form. Okay,
Okay.
but the whole thing is shown in SDB form. You just take log base 10
Divided
uh,
milliwatt.
of this whole thing divided by 1 milliwatt. 1 milliwatt is your reference. So the
Okay.
whole thing, the whole power on the right hand side, you can also show as dBm, right? The whole thing dBm.
Yes,
Now
sir.
in this next step, you after you show the whole thing as dBm, in the next step you can separate some of the terms. Maybe you have to work with one of the terms. Okay, maybe this particular term for pi by d, you need to work on that part separately. So just separate that in the next step. I mean, you can do anything in the equation. Just separate this term. It's a log term, so just separate this term. Gr also you separate. Okay, now as you
Sir,
separate in the log, yeah, so you
no,
have
sir.
like
It's clear now.
you have just say log abc by 1 milliwatt. Okay, that's what you have. In this next step, who stops you if you separate that B or C?
So, sir, it's kind of like that. We are separating all the variables and then we are doing the
Yeah,
log.
yeah. We are just keeping the
Yes, sir.
PT, the PTGT part or what you're sending from the transmitting end. Okay. Then because we have different things to consider separately. Path loss affects you in one way. The GR that you are dealing with at the receiving end, it has no bearing on what you have on the transmitting end. So this is something to work on. The responsibility, the responsibility of the engineers at the receiving end. Okay, somebody may be trying to do something to affect the path loss. Okay, so these are separate things to consider for engineers. So let us separate them so engineers can focus on different things separately and work on them. Okay, so the first term is separating what you have at the transmitting end. Okay, sometimes only PT is kept there. Okay, you
Yes,
separate
sir.
PT and then GT also you separate. So then PT will have just PT by 1 milliwatt. Then the next term will be just GT. Okay, then GR.
Yes.
That could be also another representation, the PT. Now only this term, one of these terms has 1 milliwatt, and that is usually PT or PTGT. When you keep 1 milliwatt, the practice is that you keep it with PT or PTGT. That's EIRP. Okay, so the term which you are which has the 1 milliwatt and the denominator is using that part as your reference. I mean, that should be shown as dBm, while the rest should be shown as dB. Okay,
So for the rest of the
but
part, what is the reference point for GR
no,
and PL?
well, in fact, for all of them, that 1 milliwatt is the reference.
Okay.
In fact, for all of them, because the whole thing is actually combined,
Yes.
but you are showing them separately. So when you are separating, you still have log term is there, right?
Oh yes, sir. Yes.
Log term is there. As long as you have log term, you should use the term unit dB.
Okay.
PL also has the term log 10 base log multiplied by 10. That we are not removing. Just
So
1
we are
by
just converting one unit. I mean, it's
1
suppose
milli,
it's a
1
meter,
mil,
and we are taking it millimeter in
1
one
mil,
part.
our reference 1 milliwatt, we are just keeping with, we're just showing that it is with this one, but actually we have this 1 milliwatt reference with the whole thing,
No, sir.
right? Okay.
Sir, we are initially dividing both sides by milli and then doing the log and separating each term.
Right.
Like that. Yes.
Right. Exactly. That's how you consider the whole thing. Okay.
Yes.
So, but since you are, say, your actual GR could be, say, maybe, say, if it is, for example, if it is 10,000, it's not that high though. Huh? Then you take log base 10. Okay. Or say we call it 100. GR is 100. Okay. Then take log base 10 and then multiply by 10. Then that will give you 20. So in dB, the actual GR is 100, but in dB it is 20. So when you work with dB term, then you actually put here dB in 20. Now, in the problem, I can give you your GR in dB. I can give it that it is 20. Okay.
Okay, sir.
Your PT, GT, all this information may be given in dB. Okay. But for PT, I will use dBm. For the GTGR, okay. PL may be given in dB. Or you may have to calculate, D may be given, frequency may be given, you calculate PL in dB. Okay. So most likely you'll have to work with dB in the problem. Now, this and the point for PR, it doesn't work when you set D equals to 0, right? It's not true for D equals to 0. I mean, for very small distance you can use, but not for 0. It becomes infinite then. So actually, in fact, you don't have to do that either, because people don't put an receiving antenna that close. Okay.
Yes, sir.
Or you are even not allowed to do that. You are supposed to put your antenna in the far field region, not in the near field. Okay. I mean, it's actually prohibited to use a receiving antenna in the near field region. So you have to put it in the far field region. And so, okay. Now, a lot of times, people use some reference distance. Okay. That reference distance, definitely it will be in the far field region. The minimum distance for far field, okay, is shown as DF here. DF tells you the minimum distance in the far field region. So the first reference point is chosen in the far field region, so D naught will be larger than DF. And then at that distance, you calculate your PR, or you may even measure it. Okay. Because I mean, when you measure, then few other things will be considered automatically, if that is there. Then for other distances, okay, you consider this relationship, but for the reference distance you may measure, okay, that will increase accuracy. Then for other distances, you just use this expression, okay. Then you actually have to just relate, right? For D naught, if you know, because PT, GT, GR will be constant. Now for different distances, the receipt power can be calculated just using this relationship. Okay. Just holding PT, GT, GR constant. If you know the PR for D naught, okay, PR D naught is known, then for any distance PR D, you can calculate this way, right? I mean, it's a calculation.
Yes, sir.
Okay. And please remember that PR is dropping with D and inversely proportional to D square, and PL. Okay, this part we call path loss, because that represents how much. I mean, as the denominator increases, you have more energy losses on the way. So this represents how much power you are losing because of the distance. How much power you are losing because of the distance. That is called path loss, because of the path distance you have. Okay, so it's called path loss, and that path loss is I mean, proportional to D square. Okay. Now if you want to calculate using electric field, okay, then earlier we showed that the power has an expression E square by eta, E square by eta for plane wave. Okay, so the same thing we can also do for reference distance. You calculate E, okay, ED naught, and then for any other distance, if you want to calculate E, okay, then you have to use this relationship. Then you see that the final equation doesn't have the square if you use E. Okay, so E falls by 3 dB when PR falls by 6 dB. Like when the power drops by 6 dB, your voltage drops by 3 dB. Okay, similarly, you have E drops by 3 dB if the power drops by 6 dB. Okay. Well, I have just been able to complete the first part. In the second part, we will consider reflection. How is that? Yeah.
So
Yeah.
can we continue
Yeah.
with the second part tomorrow, sir?
Yeah, we will do
We have
that.
a class now, sir. Yes, sir.
We will do that. I know, we'll do that. I just wanted to tell you what we would cover there. Okay.
Okay.
We'll consider a communication between 2 points
Sir.
with now a ground below that. Okay, so like we have 2 towers, say AB and CD, and you have transmission from A, reception at C. Okay, so there will be definitely, I mean, a link A to C that will be just like what we have considered today. Okay, so this is LOS communication link. This will have free space communication method. But in addition to that, we'll consider a ground below that, which can reflect. Ground works as a good reflector, which can also reflect the energy. So from A, energy will be incident on the ground, and the reflected energy will go to the receiver. So the power you receive there will be a combination of these two. You have to combine or sum up these two power components to get the total power. Okay, so see in this case how you can calculate. In this case again, you'll
So can we see it tomorrow?
yeah, we will.
Yes, sir.
We will.
Okay.
Okay, so well, any questions?
No, sir.
Questions for today, sir.
Sir, a request, sir.
Yes.
Sir,
Go ahead.
can you give us the PDF, sir? It would be much more convenient for us to study for the exams.
They're given
Um,
in right.
I mean the lecture materials.
No, sir. Sir, the PDF that, sir, your handmade notes, sir.
I mean what we have discussed today.
Yes, sir.
I uploaded it.
Yes, sir, you
last
uploaded
week.
it.
Yeah.
Oh, sir, I haven't checked it, sir. Sorry, sir.
Okay. Okay. Few other things that we'll be discussing even next week are all already uploaded.
Sir,
Okay.
1 minute to go. Just I'll scoot up, sir. Sir, sir, tomorrow, sir, the class will be at 11:45, right, sir?
I thought it was at 10:30. Is it 11:45?
Or 10:30?
It's 10:30, right?
It was
Yes, sir. Yes.
10:30.
Well,
My
well,
bad.
this
Sir. Yes,
year.
it was 10:30.
10:30,
It was
yeah.
10:30. Yes.
So the
So,
link that I have shared today is scheduled at 10:30.
yes. Sir.
Okay. Okay. I'll see you tomorrow.
Inshallah, sir.
Thank you very much.
Inshallah,
Thank you,
sir.
sir.
Alaikum salam.
Yes.